Welcome to the Poseidon DevBlog number 2. Today we want to talk about the electronics and software we engineered for the FAR test stand. What I hold in my hand is a breadboard with electronics on it. As you can see, there are 4 integral parts. Here on the left is the XB radio, so this ensures the communication between this breadboard and my computer. We will come to that later. Then here in the middle you can see a microcontroller. This is the TNC 4.1 with an SD slot, and mainly what it does, it reads out the load cells, which can be connected here. So we have 2 ports. Then we have the load cell drivers. I think they're HX711 2 times with a breakout board. And then they are connected via I2C to the TNC, which read them out, collects the data and stores it to the SD card and parallel sends it to the laptop. There is a communication protocol in place which standardizes the communication between the laptop and this circuit. For example, this can trigger to start recording of the data to the SD card or to calibrate the load cells. Okay, before we wire everything up, let's start with the protagonist of the show. This is a load cell, and what it does, it measures force. For example, thrust or weight. That's actually the 2 cases we are using it for our FAR test stand. You can read more about that in other blog articles. So, we plug it in. It has 4 wires, red, black, white and green, and it goes in that direction as labeled on the breakout. And then we also plug in power. As you can see, the power is from a power bank, so I don't have a physical connection between this and my computer. Now it boots up, and when we look here at my screen, I can click Start Data, and then it begins transmitting all the data collected on the fuel cell, load cell, fuel cell is something different, to my laptop. This is the according load cell which is connected. We actually have 2 ports, so you can tick here if you want to see left, right, or also both combined. I just click left because right and both don't have value because there's actually nothing connected. And if I click here, you can see that it peaks on the graph. That is good, but of course we need to calibrate the load cell accordingly because data is only relevant when it's calibrated. So here down below is the calibration section. Here we can choose which load cell we want to calibrate. In this case, the left one is ticked, that is white. Now we hold it down here and set it as 0 because no force is applied other than the own weight of the load cell. So I could calibrate 0, and then down below in the info field we will get the response, and we get here the offset. You don't have to remember that. And now we do calibrate loaded. This is a 2 euro coin and it weighs 8.5 grams, so I put it here in the end. I also input it in the GUI that it weighs 8.5 grams and click on calibrate loaded. Now we have to wait a little bit, and now we get the response. This is more or less the scale. And now when I start data again, you see that it's around 8.5. Of course, this has a little fluctuation because no measurements are perfect in this world. And if I remove it, it will go back more or less to 0 again. And for example, when I put this pencil on top, we can measure the weight, and it appears to be 24 grams around that. And when we actually do test with the test stands, of course we want to have the data for a later analysis. So I also added the function called start record. Then it starts the record locally on the computer and to the SD cards. One thing to mention regarding the SD card, that all the calibration for both load cells are also saved in the SD card. So when rebooting, the latest calibration is loaded. And for example, now I put it on, so it pikes up. And let's stop the record. And it's saved 1 copy on the SD cards, 1 copy on the laptop. And what this means that in every case, for example, the SD card fails or the transmission gets cut because of bad weather, for example, then we always have one copy of data. And if we plot the data, it looks something like here. And you can actually do stuff with it so it's interactive, or for later analysis, we actually can do it automated. And one last thing to note is we have this valve control here at the bottom, open valve and close valve. We plan to implement MOSFETs into the fast circuit to remotely control it. Currently, this feature is not implemented. Okay, that's it for today. I hope you found it interesting and learned something new. Until the next time.